In this video, I'd like to give you a quick demonstration on how to extract bottom-up models from a phase lock loop circuit using MODELZEN. This example is a part of our tutorial named xmodel_PLL. So if you'd like to follow this demo, you can first copy the tutorial directory into your local directory, then go into the xmodel_PLL subdirectory, source a setup script depending on your shell type, and launch Cadence Virtuoso. The top-level cell view of the phase lock loop example is located in this frac and PLL library with the cell name PLL. This phase lock loop, in short PLL, is made of a phase frequency detector, charge pump loop filter, voltage-controlled oscillator, and a frequency divider. This particular PLL is called a fractional end PLL because it can produce an output frequency which is a fractional multiple of the input frequency. Let's take a look at the phase frequency detector first, in short PFD. A PFD measures the phase and frequency differences of the two input clocks and produces the output pulses up and down. In this example, the PFD is implemented with two resettable D flip-flops and an AND gate for the reset path. Let's extract a bottom-up model for this circuit. There are various kinds of models and properties you can set on a schematic to control the way MODELZEN generates the model. For example, knowing that the input and output ports of this PFD circuit propagate digital values, we can set the signal type of these pins to X-bit so that the MODELZEN generates a model with the X-bit type input and output ports. Now, to extract the model, simply click this icon to run MODELZEN. MODELZEN first extracts the SPICE netlist from the circuits and opens this dialog window asking for your confirmation. When you click OK, MODELZEN will then start analyzing the netlist and run characterization on each of the devices. And finally, it will put together the resulting models to build the final model. Once the model generation is completed, MODELZEN then imports the model into the Cadence database into an xmodel view of the same cell. Let's open it to see what this model looks like. MODELZEN by default generates a structural model, and you can see that the PFD model has a set of logic gates such as D flip-flop, NAND gate, inverter, just like in the original circuit. And each of the logic gate is described using the circuit primitives of xmodel. And the input ports, clock ref, clock FB, and the output ports, up, down, and up, are declared as X-bit types, and MODELZEN has inserted these connect primitives to convert them into the internal X-real type signals. Let's try to run a simple simulation with this PFD model. We have a test bench named TBPFD, and this test bench feeds two clocks with slightly different frequencies to the PFD so that the amount of phase difference gradually shifts over time. To run the simulation, open this xmodel test bench editor, generate a netlist, and launch the xmodel simulation. Once the simulation is completed, open the X-Wave waveform viewer to check out the results. You can see that the phase difference between the two input clocks gradually changes, and the duty cycles of the two output pulses, up and down, also change gradually, and the net pulse width indicates the phase error at each given time. The next block of the PLL is the charge pump loop filter. A charge pump enables either an up current or a down current when the up or down inputs from the PFD is asserted, respectively, and the current develops a voltage across this RC-based loop filter. This voltage then serves as a control voltage to the next circuit block, the voltage-controlled oscillator. Knowing that the inputs up and down are digital, we set their signal types as X bit and generate the model by clicking the X model icon. Next, the voltage-controlled oscillator, or VCO in this example, is implemented as a 5-stage ring oscillator. This cell also includes the bias generator and a clock buffer to generate a full CMOS level output clock. Again, we set the signal type of this output clock as X bit and generate the model. Let's run a quick simulation with this VCO model. There's a test bench named TB-VCO, and this test bench feeds a sinusoidal input to the VCO and observes the output clock frequency. When you run the simulation, and view the simulated waveforms, you can see that the frequency of the output clock changes as the input varies. Now, we have generated models for all the major blocks except for the frequency divider. This example contained in the tutorial intends to synthesize this frequency divider from the Verilog models, and therefore we do not have its circuit schematics. So we'll use the Verilog models for this frequency divider when simulating the whole phase lock loop. It implies that we need to build an X model netlist that selects the Verilog model for this frequency divider and selects the MODELZEN generated models for the rest. You can do so by opening the Virtuoso Hierarchy Editor and choosing the desired view for each cell. Now, select the test bench name TB locking 0 of the PLL cell, which simulates the locking transient of this PLL. Netlist the test bench and launch the X model simulation. This simulation will take quite a while. The simulation has finished and it took about 34 minutes. The waveforms show that the PLL successfully reaches its lock point about after 40 microseconds and produces a frequency of 400 MHz, which is 13.333 times the 30 MHz input frequency. This simulation was rather slow to our standards, and it was because the VCO model oscillating at 400 MHz constantly generates a lot of events during the simulation. We can make this simulation much faster by modeling this VCO as functional models using the MODELZEN's new User-Defined Model Interface, in short, UDM. With this UDM interface, you can generate higher abstraction models, such as functional models, for any selected parts of your circuit. To map this VCO to a UDM, select the instances that make the VCO and select a pop-up menu, Models and Properties, or you can simply press Ctrl Q. Then select the model VCO_V1 and define the mapping between the nets on the schematic and ports of the model, and also define these parameters that control the characterization. When you press OK, this mapping information gets stored on the schematic. Now you can generate a functional model from this circuit using the same flow of MODELZEN. That is, simply click this MODELZEN icon. Let's take a look at this new model. The generated model for the VCO now contains a UTM instance instead of the circuit primitive seen before, and the definition for this UTM follows next, which describes this VCO circuit as a piecewise linear function primitive followed by a frequency to clock primitive. These numbers describe the voltage to frequency characteristics of the VCO, which are extracted from the SPICE simulation run by MODELZEN. Now, let's run the same test bench using this new model. The simulation now takes about 2 minutes, which is about 17x faster than before. This UTM interface of MODELZEN gives a simple way to speed up your simulation by mapping only a few critical circuits to functional model. In summary, MODELZEN is a tool for automatically extracting bottom-up models from your circuits, and with the generated models, you can perform efficient verification of your circuits all in System Verilog. If you'd like to learn more, please visit our website at www.scientificanalog.com. Thank you.